Start our tutorial for this morning. Right, so as I informed yesterday, we will have a tutorial session today. So I will cover tutorial starting from chapter 2. We do not have any tutorial for chapter 1 because chapter 1 is mostly explanation and the derivation of the equation. So we don't have tutorial for chapter 1. We will straight away go to tutorial question chapter 2. So if you are looking for the question is already in the VLE as well as in the Teams folder, and in the questions I already actually included the final answer as well in the question. So you can actually attempt it by yourself later on, and even if you attempt it later on, you still have the final answer for the comparisons of to know that whether you're doing it correctly or not. Okay, so I will start for the questions for this morning. Right, so I will read out the questions, and then I will explain the steps. Okay, and then I will give you a little bit of time, maybe 1 or 2 minutes for you to do the calculation if you have the paper and the pen with you, and then I will proceed to the next question. Okay, so for the first question for this morning, we have an equal molar of gas mixture A and B. Okay, so it's very important in engineering questions is basically understanding the question first. Okay, so most of the time, students are not able to solve the questions mostly because unable to actually understand the question in the beginning. So it's very important for you to understand the question. So in the first part, it says equal molar of gas mixture A and B. So what does this mean? Meaning, initially in the reactions, in the reactor, we have two reactants. Okay, so how do I know it's two reactor? Because they say equal molar of gas mixture A and B enter the reactor. So you know when it enters the reactor, it must be it is the reactant. Okay, so first, second, you know there's two reactant A and B. Okay, third, they say it's a gas mixture. So there's a few information that you need to understand. First, is enter the reactor. Second, it consists of two reactants A and B. Third, it is gas phase. Both are in gas phase. And fourth, it says equal molar. Okay, equal molar means they are entering the reactor in equal molarity, or molarity we can also say concentration. So we do not know what is this concentration. It can be 1 molar to 1 molar, 2 molar to 2 molar, 3 molar to 3 molar. We don't actually know the actual concentration, but we do know they are equal in concentration. So this information actually tells us we can actually know the molar percentage of these two compounds initially. Okay, if you have equal molarity, okay, for example, let's say I put it as, we assume 1 molar, 1 molar. So in terms of percentage, it will be 50% A, 50% B. This percentage is in terms of mole percent, meaning initially the mole percent of A is 50%, the molar percent of B is also 50%. Okay, but you know, right, in calculation, we will we will use in terms of fraction, not in terms of percentage. Okay, so in terms of fraction, it will be mole fraction of A initially 0.5, mole fraction of B initially is also 0.5. Okay, 50%, 50%. So mole fraction here 0.5, 0.5. So that's the first thing that you can deduce from the very first sentence. Okay, next they says enters the reactor at 250 dm cube per second. So when you see the number and the unit, it's important for you to know as well what does that mean. Okay, so from the unit, you know the unit dm cube is volume, second is time. So volume per time is volumetric flow rate. But you do understand that volumetric flow rate, they has initial and final volumetric flow rate. Okay, sebab volumetric flow rate ni ada initial, you have also volumetric flow rate at at the final volumetric flow rate. So since they say enter the reactor, so this is initial volumetric flow rate. So it's epsilon naught 250. Okay, so far we have few information. Mole fraction, initial mole fraction. A equals to initial mole fraction of B equals to 0.5. Second, we know the epsilon naught as 250 dm cube per second. Next, temperature 125 Celsius. Celsius you already know lah, it's definitely temperature. So similar concept. Temperature in the reaction also, we have initial temperature and final temperature, because if you learn before in chemistry, reaction pun we have endothermic, exothermic reaction, meaning during the reaction, they may be heat released or heat absorbed to the reaction. So when you have this, naturally the temperature also will change, meaning initial temperature, final temperature is not necessarily the same, except if they say it is an isothermal reaction. Kalau isothermal reaction, iso means same, thermal means temperature. If the reaction is isothermal reaction, someone mic is not muted, can you please check? All right, thank you. Okay, so if it's isothermal reaction, okay, then the temperature is the same. Means there are no changes in the temperature. If it's non-isothermal, then they can be temperature change. So what is this indicator? Meaning, even the T also you have to indicate T naught, which is initial temperature, or T, final temperature. So in this case, since the kata enters the reactor, so this is T naught. Okay, naught is to indicate at time 0 or at the time before the reaction taking place. Okay, so done. We got epsilon naught, we got T naught. Okay, they say calculate the initial concentration and initial molar flow rate of A. So what do they want to find? They want to find initial concentration of A. So you know concentration, the symbol is C. Then you know concentration, it must be specific to the compound. Since they say this is for compound A, C subscript A. Then don't forget concentration pun you have initial and final concentration. Since they say initial concentration of A, so they want us to find Ca naught first, one. Second, they want us to find initial molar flow rate of A. So kalau molar flow rate, we use F. Molar flow rate of A, F subscript A. Initial molar flow rate of A, Fa naught. So the question wants us to find Ca naught. The question wants us to find Fa naught. Okay, the two things that we need to find. So let us go to part A of the question. The part A of the question says, if, okay, find Ca naught and Fa naught if the initial partial pressure of A is 250 kilopascal. So they want us to find initial concentration of A and initial molar flow rate of A, Ca naught and Fa naught, if the partial pressure, the initial partial pressure of A is 250 kilopascal. Okay. So how do we solve this question? Right. So first of all, what is this 250 kilopascal? This 250 kilopascal is the pressure that is owned by A, or the pressure of A initially in the reactor. So pressure we use P. For compound A, we use A subscript A. So P subscript A. And since this is initial partial pressure, we got naught. So what 250 is actually Pa naught. Okay, so Pa naught is 250 kilopascal. Okay, so how do we find the initial concentration? Okay, so if you remember previously, I taught you in chapter 2, this is chapter 2, okay, for gas phase, only and only gas phase, there is an equation that can be used to find the initial concentration. So why we say it's only for gas phase? Because this equation is based on the ideal gas law. So that's why if the equation is based on ideal gas law, it means the law is only applicable for cases of which it is gas phase. So if you have liquid phase, you can no longer use this equation because this law or this equation only and only applicable to gas phase. So if you remember, the equation is given as CA0 equals to PA0 per RT0. Okay, concept dia, I want to find concentration of A initially is equal to the initial partial pressure of A divided with R, gas constant, multiply with the initial temperature T0. Okay, so straightforward, this is not that difficult. PA0 we know is 250 kilopascal as given in the equation. I make it bigger, this is a bit too small. Okay, so you know PA0 is given as 250 kilopascal, right? Next, gas constant. So gas constant, all right, this is also a question that sometimes students will get confused because as you know, we have different combinations of gas constant value because it depends on the unit. So if you Google pun, you realize there's a lot of R value, you know, because it depends on what unit that you want to use. So let's say you want to use for ATM, ATM per liter, Kelvin, so on and so forth. Dia ada combination yang berlainan. Okay. But always student will ask, how do we know which R that we can use to solve the question? So for me personally, dia tak ada salah atau betul because whatever unit that you use, whatever R value you use pun okay because at the end, as long as you can do the unit conversion, the answer will still be the same. But to shorten the step or to save your time, in my opinion, usually I will choose my R value based on the R value punya pressure unit. I will see the pressure unit of my R value and I will choose the one that is consistent with my pressure unit in the question. So for example, in this question, they give the pressure as 250 kilopascal. So I will find the R that has kilopascal. So that one is actually 8.3144 kilopascal dm cube per mole Kelvin. So why I do this is because I want to automatically cancel my pressure unit straight away. So you can see I can already cancel my pressure unit, my kilopascal directly this way. Sorry, I can directly cancel my kilopascal unit. Done. Okay. Next, I have to multiply with T0, initial temperature. Okay. This part you have to be careful because you realize our gas constant, the unit of temperature is Kelvin. So naturally, the unit of our temperature in the calculation, we have to convert to Kelvin immediately. Ataupun we have to convert the temperature to Kelvin. So because the temperature given to us was 125 Celsius, kan? So this 125 Celsius, I will convert to Kelvin. So if you remember, conversion factor for temperature from Celsius to Kelvin is very easy. You just plus 273.15. Okay, again, to convert from Celsius to Kelvin, if you check conversion table, it's just by adding 273.15. So by doing this, I can now cancel the Kelvin unit as well. For my R value, for my gas constant, R value Kelvin, I can cancel with my temperature T0 unit already. So I cancel my pressure unit, I cancel my temperature unit. You realize that the unit now that is left is actually dm cube per mole at the bottom. Okay. So when you calculated this, make sure you do this properly. You will get your final answer 0.076. But what about the unit? So don't forget, sometimes Pak ni pun kadang-kadang mathematics you might forget. When you have 3 layers of variable, macam case ni kalau kamu perasan dia adalah 1 per B per C. So when you have 1 per B per C, the third layer of the unknown will goes to the top. So 1 per B per C will become C per B. Sebab tu you realize the unit mole now goes to the top. The unit dm cube is at the second layer. Yang ketiga tu naik ke atas sebenarnya. So you get finally the final unit mole per dm cube. So I always tell you, right, in a way for you to check your calculation, tengok unit. If your unit is mole per dm cube, mole per volume, which is actually concentration, and it is indeed true, you want to find concentration, most likely your answer is correct. Okay, so most likely kalau unit tu consistent with the dimension of what you want to find, most likely the formula that you use is correct. Okay, so next part, they want us to find FA0, the initial molar flow rate of A. So to find initial molar flow rate of A, there's only one correlation. Okay, remember I told you kalau gas phase, kalau flow system, the correlation ada for concentration, molar flow rate, volumetric flow rate. The correlation is given as FA0 equals to CA0 multiplied by V0. Okay. Even if, let's say, you know these three are correlated, molar flow rate, concentration, volumetric flow rate are correlated to one another. Let's say you forget dia multiply ke, divide ke, so on and so forth. Like I told you, just do unit cancellation. Kalau kamu katakanlah you're not sure, you try first to multiply. If you see the unit cancellation, you can cancel the unit, you get the correct dimension that you want, most likely you are correct. So for example, in this case, I put it as FA0 equals to CA0 multiplied with epsilon naught. Okay, means initial molar flow rate of A equals to initial concentration of A multiplied with initial volumetric flow rate. Okay, so let's say we multiply. So initial concentration we get from part the above part as 0.076 mole per dm cube. We multiply with the initial volumetric flow rate 250 dm cube per second. So you multiply. You can see that I can cancel the volumetric flow rate unit. Sorry, not volumetric flow rate unit. I can cancel the volume unit. You can see that I can cancel my dm cube. I can cancel with another dm cube. I'm left with mole per second. So again, I want to find molar flow rate. Mole per second, mole per time. It is indeed molar flow rate. So very likely your calculation is correct. So you get the final answer as 19 mole per second. So done for part A. I will go to part B. Then I will give you 1 or 2 minutes to solve the equation. Okay, I will go to part B first. So part B, they say they ask us to calculate again CA0 and FA0. But in case B, they tell us the initial total pressure of the system is 1500 kilopascal. So what's the difference part A and part B? Part A, they give us the pressure of A, initial partial pressure of A. Means yang 250 tu is the pressure that is from A and only A. In part B, they tell us the initial total pressure of the system is now 1500 kilopascal. So this 1500 kilopascal is the pressure that comes from A and B. So you don't forget this part. Pressure, kalau kata total pressure, maksudnya kita kan ada dua compound A and B. So the total pressure of both these compound is 1500. So in the calculation, we want to find concentration of A. We cannot use this 1005 sebab 1005 ni ada juga terkandung pressure of B. If I want to calculate concentration of A, dia mesti only and only pressure that comes from A. So how do we solve this? Okay, that's why we learned before, and you learn this in CPP and you learn in other courses, we can use the correlation of Raoult's law. Okay, so how do we use this correlation? Because Raoult's law mentioned, kalau nak tahu pressure A, okay, katakan nak tahu pressure, let's say in our case, you want to know the pressure of A, is equal to the mole fraction of A multiplied with the total pressure. Okay, so you got PA0 will equal to YA0 multiplied with P0. YA0 ni adalah mole fraction A initially. Okay, so dalam soalan kan they say equal molar. Tadi kan dia kata equal molar initially means 50% mole A, 50% mole B. Okay, so kalau kita ada 1500 ni, actually this 1500 is consists of 50% A, 50% B. So by right, the pressure of A is 750. Pressure of B is also 750 kilopascal. Okay, so that's why in the equation it becomes CA naught now equals to YA naught multiplied with P naught. Okay, sebab YA naught multiplied dengan P naught is actually equals to PA naught. Mole fraction A darab dengan total pressure adalah sama dengan pressure E. So that's why you do YA naught 0.5. If you are confused, Y is to use to signify mole fraction. A to signify compound A, not to signify initial mole fraction of compound A. So 0.5, 50% dalam bentuk fraction 0.5 multiply with the pressure 1500 kilopascal, the total pressure. So I hope you know or you remember, kalau fraction dia tak ada unit, dimensionless. Sebab tu 0.5 tu tak ada unit, tak ada dimension. Okay, multiply with 1500 kilopascal divided by similar concept R value. So since my pressure is in kilopascal, I will also use the R value with the kilopascal unit. So 8.3144 kilopascal dm cube per mole Kelvin. So by doing this, I can already cancel my kilopascal unit. Next step, multiply with T naught. The temperature is still the same, 125 Celsius, but since my R value, the temperature unit is Kelvin, so I straight away convert my temperature from Celsius to Kelvin. So from 125 to convert to Kelvin, you just add 273.15. That's the conversion factor. So now I can cancel kilopascal, I can cancel my Kelvin, I'm left with once more mole per dm cube, which is my concentration unit. So you calculate the number, you will get 0.2266 mole per dm cube. Subsequently, to find FA naught, that's straightforward. FA naught is still the same. CA naught multiply with V naught, but of course don't forget my CA naught dah berubah because my new CA naught is 0.2266. So I multiply 0.2266 mole per dm cube, multiply with my initial volumetric flow rate, which is again the same 250 dm cube per second. Okay, again, if I do unit cancellation, I can cancel my dm cube. I'm left with mole per time, mole per second, which is molar flow rate. So most likely your answer is correct. So let's say katakan kamu confused. FA naught ni sama dengan CA naught multiply V naught ke, CA naught bahagi dengan V naught ke. Let's say you're confused, you just do the unit cancellation. If your final unit is not consistent with what you want to find, then you have to recheck because that means indicate that you are doing the wrong calculation. Okay, so I'm done for question 1. So I will give you about 1 to 2 minute break. Okay, not break. I will give you 2 minutes to try to solve this by yourself. If you have a pen or paper with you, I will come back in 2 minutes time. Okay, so done for question number 1. Okay, I will continue to question number 2. For those yang tak sempat, it's okay because as I told you, the final answer is already available in the question as well. Okay, so just maybe if you miss out, later just watch the video a little bit. Okay, then you can do it by yourself. But I really advise you guys jangan setakat tengok video and then hope, jangan setakat tengok video and think that you can do it later, ataupun maksudnya tengok video tapi tak buat sendiri, you didn't do it by yourself and then you wait until test baru nak buat. Please don't, I would not recommend to do this because reaction ni memang actually you really need to do the calculation by yourself. Of course you can watch the video and to refer while you're doing it, but you have to really understand question tutorial takkan keluar sebiji dalam test atau exam. You can ask your seniors. I will not come up directly the question from tutorial to the exam and test. But if you understand the questions, you can do definitely the question in the test or exam. Okay, so that's the part you have to understand. Kamu kena betul-betul faham soalan sebab I was change a parts of the question. But if you really understand, that is not a problem. Tapi if you don't really understand the question, you just do it by looking at the video. It might cause you a little bit problem later when you attempt the question in the test or exam. So for reaction, actually the key is understanding information. Then only you can do the questions correctly. Okay, so let us go to the second question. The second question says, a mixture of 30 mole percent SO2 and the balanced air is charged to a flow reactor in which SO2 is oxidized to form SO3 at the initial rate of 10 mole per second of O2. Okay, so you see from the very first question, you have a few information you need to digest. So first information, dia kata initially, sebab dia kata charge to a flow reactor. Initially yang masuk dalam reactor tu consists of 30 mole percent SO2 dan balance dia air. Okay, so maksudnya, alright, so you see the question, the chemical reaction is between oxygen gas and SO2. So SO2 punya mole percent is 30%. Okay, and the remainder percent, 70% is air. So kenapa dia guna air walaupun our reaction is with oxygen gas, but they do not pump in pure oxygen gas. Instead, they pump in air because air contains oxygen as well. So air contains a certain portion of oxygen and certain portion of nitrogen and carbon dioxide sebenarnya. So instead of using pure oxygen, the question says they are using air. But bear in mind, walaupun kita guna air, but the gas that is reacting in the reaction is only oxygen gas. So yang 30% SO2, the remainder 70% is air, not oxygen gas. Okay, next. Dia kata oxidize to form SO3 at the initial rate of 10 mole per second of O2. So what is this 10 mole per second? So first dia kata mole per second, mole per time. So mole per time, molar flow rate. Okay, next dia kata initial. So this is initial molar flow rate. Then dia kata oxygen gas. So this is initial molar flow rate of oxygen gas. But normally kita akan calculate dalam bentuk ABC, right? We always calculate FA0, CA0, so on and so forth. So how do we know which is A, B, C and D? As I told you, our A is always the limiting reactant. Okay. If they do not state which one is limiting reactant, because we have two reactants, SO2 and O2. If the question did not state which is the limiting reactant, you can and may assume the first compound in your chemical equation as your A. So maksudnya oxygen gas ni adalah A kamu, SO2 is your B, SO3 is your C. So therefore, this 10 mole per second of O2 is actually your FA0. Okay, sebab oxygen gas adalah A kita, so it become FA0 equals to 10 mole per second. Okay, so now the question says, again, given the total initial pressure of the system as 15 atm. So again, dia kata initially total pressure system saya 15 atm. So this 15 atm is the pressure from SO2 as well as air. Okay, so 15 atm ni adalah tekanan udara dan juga tekanan SO2, which we don't know how much, but we know the total pressure 15. Okay, and dikata temperature 230 Celsius. So 15 atm ni adalah P0, initial total pressure. Okay, T0 230 Celsius. So P0 15 atm, T0 230 Celsius. Dan dia kata sekarang, air contains 79 mole percent nitrogen gas and the balance oxygen gas. So remember just now, kita ada 30% SO2, kita ada 70% air. So dalam 70% air ini, okay, ada 79% N2, M bagi 21% O2. So kalau bayangkan dalam 70% ni, dalam 70% air ni, dia punya composition dia pula terbahagi kepada 2, which is 79 mole percent N2, 21 mole percent O2. Yang 21 mole percent ni lah sebenarnya yang digunakan untuk the reaction. Okay, what about nitrogen? So in this case, okay, nitrogen is also known as an inert. Means dia takkan, walaupun dia ada dalam sistem, okay, dia ada pressure dalam sistem, but they will not be involved in the reaction. So that's why a lot of reaction that uses oxygen, dia akan guna air. Sebab air tu ada oxygen, ada nitrogen, a large amount of nitrogen, but this large amount of nitrogen will not be involved in the reaction. They have traces amount of carbon dioxide. I think it's about 0.03, very trace amount, so they would not really affect the reaction. Okay, done. Right, so now they say the question, calculate the initial concentration and initial volumetric flow rate of oxygen gas. Okay, dia nak tahu CA0, O2 is our O2 is our A, right? So dia nak tahu CA0 dan epsilon naught. Okay, so they want to find CA0 and epsilon naught. Okay, so again, same concept. Kalau kita nak cari concentration, initial concentration, and they say it is gas phase, directly you know that you need to use the ideal gas law punya equation. Asalkan dia gas phase, nak cari concentration, you can straight away remember that we will use the equation, the ideal gas law equation, which state CA0 equals to, since dia beri kita initial total pressure, which is P0, don't forget you have to multiply with YA0. So become CA0 equals to YA0 P0 per RT0. So yang pengatas ni kamu just ingat je. Kalau dia beri kita terus tekanan A, initial pressure of A, dia jadi PA0. Kalau dia beri kita total pressure initial, P0 tu kita kena darab dengan YA0. YA0 P0 sebenarnya sama dengan PA0. Kalau dia beri PA0 terus guna. Kalau dia beri P0 multiply with YA0. That's the only thing that you have to understand. So kalau ada soalan, make sure you check. Is that PA0 or is that P0? Kalau P0 mesti darab dengan YA0. Kalau diberi terus PA0 terus ganti je, tak ada masalah. Okay, then pembawa dia is always the same divided by RT0. Okay, now the top part yang menjadi masalah. What do I mean by the problem? How do we know the initial mole fraction of A in the system, ataupun how do we know berapa sebenarnya persen oxygen gas initially? Okay, dia ni yang tak straightforward. It's not so straightforward sebab persoalan dia initial saya ada 30% SO2, 70% air. Dalam 70% air ini ada lagi terbahagi kepada 79% N2, 21% O2. Kamu kena ingat yang 79-21 ni adalah percentage dalam 70 itu. Dia tak mewakili percentage keseluruhan for the whole system that also include the SO2. So bila kita nak kira mole fraction oxygen gas, which is YA0, kita kena kira berapa fraction dia terhadap keseluruhan sistem which include the SO2. So how do we calculate this? Okay, so first of all, you know SO2 punya mole fraction 0.3, 30%. Therefore, air punya mole fraction 0.7, 70%. Hence, how much is my mole fraction of oxygen gas, which is my YA0, dia akan sama dengan in my 70% air, I have 21% O2. So saya darabkan saja dari dalam 70% air saya ada 21% oxygen gas. So I multiply these two, I will get 0.147. Apa maksud 0.147? Maksudnya, dalam keseluruhan gas saya yang ada SO2, ada O2, ada M2, tiga-tiga gas ni sebenarnya, oksigen saya sebenarnya hanya mewakili 14.7% or fraction 0.147. Okay, tu sebenarnya maksud dia. You cannot take directly the 0.21. Kenapa tak ambil yang 0.21? Sebab 0.21 tu, 21% tu, hanya yang dia ambil kira yang terangkum dalam udara sahaja. Tapi kalau kita nak tahu keseluruhan dalam sistem, kita kena ambil kira juga yang termasuk dengan SO2. Sebab tu kita akan kira dalam 70% air ada 21% O2. That's why you multiply these two, you will get the mole fraction of oxygen in the overall system as 0.147. So you just multiply 0.147 with 15 atm, the initial total pressure. You divide with, again, not our gas constant value. So in this question, our pressure unit is ATM. So I will find the gas constant value of R with the ATM unit. So happen kalau kamu check, the only R with ATM unit is actually 0.082 ATM dm cube per mole Kelvin. So by using this R value, dah berlainan kan, tadi kita guna 8.3144 kilopascal dm cube per mole Kelvin. When it's ATM, it becomes 0.082 ATM dm cube per mole Kelvin. So by doing this, I can already cancel my ATM unit. Okay, so let's say lah kamu terfikir, katakan saya nak guna 8.3144 kilopascal dm cube per mole Kelvin. Boleh je, but you have to add one more step to convert the ATM to kilopascal. That's why you do that, final answer masih sama, tapi kamu tambah satu kerja lah sebab kamu kena convert. Kalau kamu tak convert the kilopascal to ATM, your final answer will be wrong. If you convert, your final answer will be the same. But you will add a few minutes of calculation dah kalau kamu terpaksa convert lagi. Sebab tu, pilih R value, look at the pressure unit, choose the R value with the same pressure unit, you save already one step technically. Okay. Then, multiply with T0. So again, nak multiply dengan T0, tengok unit R temperature in the R value. So in the R value, unit temperature dia Kelvin. So naturally, I convert straight away my temperature from Celsius to Kelvin. They give the cell temperature initially was 230 Celsius. So I just plus 273.15, I already converted it to Kelvin. So Kelvin punya penukaran senang je, tambah je 273.15. Then straight away you can do the calculation. You can see that lastly my unit still in the form of mole per dm cube, mole per volume, concentration, which is what I want to find. So the final answer will be 0.053 mole per dm cube. Okay, so this question is not that difficult, just that part yang nak tahu mole fraction oxygen itu can be a problem if you don't understand the concept of ada air, dalam air ada percentage lagi, tapi kena kira dalam percentage, dalam the context of the entire system punya mole fraction. Okay, done. So next part, they want us to find epsilon naught, initial volumetric flow rate. So part ni pun kamu dah ingatkan tadi kita dah solve, kita cari FA0 kalau diberi CA0 dan V0. Soalan ni kita tahu FA0, kita dah cari CA0, we want to find epsilon naught. So kalau kamu if you remember, kalau kamu ingat, dia terbalik je lah formula dia kan. So formula dia become epsilon naught equals to FA0 divided by CA0. Kalau kamu confused, tengok originally kan macam ni, FA0 equals to CA0 multiply with V0. So if I want to find, epsilon naught. So kalau nak cari epsilon naught sama dengan FA0 divided saja dengan CA0. So let's say you forget FA0 bagi CA0 ke, CA0 bagi FA0 ke, CA0 multiply FA0 ke, just do unit cancellation, the easiest one for you to know. So when you do the unit cancellation, you can see I can cancel the unit of mole. I can cancel the unit of mole. Then my dm cube goes to the top. I will get dm cube per second. dm cube is volume. Second is time. Volume per time. Volumetric flow rate. So most likely jawapan kamu betul lah. So you get the answer 188.68. Okay, so that's all for question. There's one more question for part B. Question for question second, part B. So they say calculate the conversion of oxygen gas if given the outlet flow rate as 5.55 mole per second. So they want us to find conversion, but they want the conversion in the form of percentage. Okay, and they beri kita outlet flow rate 5.55 mole per second. So again, mole per second, mole per time, molar flow rate. Dia kata outlet molar flow rate. So dia beri kita FA. So kita tadi dah tahu FA0 kan, dalam soalan FA0 given as 10 mole per second. Tu initial molar flow rate. Part B ditambah lagi, dia beri kita outlet molar flow rate. Kita tahu FA0, kita tahu FA. So we can directly find the conversion lah, straightforward. Conversion equals to in minus out divided by in. Inlet molar flow rate FA0 minus dengan outlet molar flow rate FA, divide again with the inlet molar flow rate FA0. So 10 minus 5.55 divided by 10 again. And since they want in percent, you have to multiply with 100%. Dalam pengiraan, kalau kita tak multiply dengan 100%, dia menjadi fraction. Dia nak dalam percentage, darab sajalah dengan 100%, you get in terms of percent. So when you calculate correctly, you will get in terms of percent, 44.5%. So done for question number 2. So again, this not so difficult. Hold on, I don't think it's that difficult. But again, the understanding on the mole fraction is very important in order for you to solve. So katakan you're not sure about the mole fraction. Okay, kamu kira YA0 tu salah, memang the entire question will be wrong. So be very careful about this matter. Okay, so I give you again as usual 2 minutes of a break for you to attempt the question. If you have it in front of you, I will come back in 2 minutes time. Okay, alright. So done question 1, question 2. We will proceed to the next question. So next question ni dah on the design of the reactor. So question 1, question 2 is just introductory. Now we go to the question that touches on the Lorentz-Spear plot ataupun dengan table yang kita dah belajar how to find the volume. Okay, the question says the gas phase reaction. Kejap saya nak tukar kepada besar. Okay, the gas phase reaction is given as follows. Okay, using the Lorentz-Spear plot for the reaction. So this is the Lorentz-Spear plot. Determine the inlet molar flow rate of a single 30 dm³ single PFR and a 30 dm³ single CSTR to achieve final conversion of 20%. Okay, so soalan senang je. Dia beri kita Lorentz-Spear plot. So don't forget, Lorentz-Spear plot dia punya karakteristik yang paling penting. Y-axis dia is 1 per minus RA. X-axis dia adalah X. Okay, so 1 per minus RA versus X. Okay, dia kata lagi, dia suruh kita cari inlet molar flow rate. Dia nak kita cari FA0. Okay, kalau diberi volume reactor kita adalah 30 dm³ 1 PFR or 30 dm³ 1 CSTR. So I have 1 PFR 30 dm³, 1 CSTR 30 dm³, dan dia beri kita conversion 20%. Means my X is 0.2. So dia beri kita X 0.2, volume CSTR 30, volume PFR 30. Dia nak kita cari FA0 untuk PFR dan juga FA0 untuk CSTR. So how do we do this? Okay, so kalau you remember, okay, kita cari one by one. Kita kena cari FA0 untuk PFR, kita kena cari FA0 untuk CSTR. You have to remember, reactor berlainan, design equation berlainan, FA0 definitely will be different already. Okay, so we start first with PFR to find the FA0. Okay, so hopefully you still remember. Yesterday we learned this a little bit already. Volume PFR equals to FA0, that's the equation, integrating from 0 to 0.2. Kenapa? One single PFR, they are converting from 0 to 20%, 0.2. Sebab tu jadi 0 to 0.2 dx per minus RA. So then you remember this part, we have to solve in the form of Simpson 1/3 rule. So it become FA0 delta X per 3 in bracket 3 points. So 1 per minus RA when my X is 0 because my lower limit is X saya adalah 0. So 1 per minus RA when my X is 0 plus 4 per minus RA at my middle conversion. So my initial conversion was 0, my final conversion 0.2, my middle conversion will be 0.1. That's why it become 4 per minus RA when my X is 0.1 plus 1 per minus RA at my final X which is 0.2. Sebab tu titik last is 1 per minus RA when my X 0.2. So done. Okay, so then we solve the question. Okay, then you see from to get the 1 per minus RA, you have to look from the Lorentz-Spear plot. Okay, jadi macam besar sangat. To find the 1 per minus RA, you have to find from the Lorentz-Spear plot. Means when my X is 0, 1 per minus RA is 2.22. Next, when my X is 0.1, my 1 per minus RA 2.7. Next, when my X is 0.2, 1 per minus RA is 3.33. So you look from the plot, you get the value, you just substitute inside. So volume PFR 30, kejap. Dia macam kejap sangat. So volume of my PFR 30 dm³. Okay, given in the question, we want to find FA0. FA0 adalah apa yang kita nak cari. So FA0, we leave it as it is. Kamu kena ingatkan dalam equation I taught you, in mathematics equation, if you have one equation, you only can solve it if you only have one unknown. Kalau kamu ada lebih daripada satu unknown dalam soalan, in the equation can never be solved. One equation, one unknown, you can solve. One equation, more than one unknown, you can never solve. So means other part of the equation, semua kamu dah kena tahu nilai dia. So I already know V, dah tahu volume. FA0 I want to find, so FA0 I leave it. Delta X per 3. So delta X per 3, as I told you, right? Delta X is the gap or the difference between initial X to the middle X or the middle X to the final X. So my initial X was 0, my middle X was 0.1. So the difference is 0.1. Or at the back, my middle X 0.1, my final X 0.2. The difference is still 0.1. So delta X 0.1 divide by 3. Formula dia kata mesti divide dengan 3. So we divide by 3. In the bracket, substitute in the value. When my X is 0, 1 per minus RA 2.22. So replace 2.22. Straight away ganti nombor sebab 2.22 itu adalah 1 per minus RA apabila X saya kosong. Plus 4. Don't forget ada 4. So 4 multiply with 1 per minus RA when my X 0.1. From the plot, when my X 0.1, 1 per minus RA saya adalah 2.7. So 4 multiply with 2.7 plus 1 per minus RA when my X 0.2. So when my X 0.2, 1 per minus RA dia adalah 3.33. So you replace into the equation, alright? You solve it because now you are left with only FA0. Okay, so kalau kamu nak buat pembatalan unit pun boleh. You realize you can cancel your dm cube unit. You are left with mole per second. So of course lah, mole per second, mole per time, molar flow rate. So you calculate this correctly, you get your FA0 55.05 mole per second, which is initial molar flow rate of A for the PFR. Okay, so soalan ni sebenarnya tak susah. Kita pun dah pernah bincang dalam kelas. Tapi part yang don't make mistake yang kalau guna plot, nilai itu adalah 1 per minus RA. So kamu straight away guna nilai tu, jangan bahagi dah. So macam kalau student confused bila guna plot, bila guna table. Kalau table nilai dia minus RA. Kalau plot 1 per minus RA. So don't forget and confuse that part. Okay, so next question. CSTR. CSTR lagi senang because the equation is so much easier. So for CSTR, design equation dia, kamu kena ingat, dia start dengan design equation dia. So design equation dia, volume CSTR equals to FA0 multiply with X divide dengan minus RA at your X that you want to find. Okay, so dalam soalan ni, volume CSTR dia dah diberi 30. Same volume as the PFR, 30 dm cube. FA0 I want to find. So again, FA0 is what we want to find. So means the rest tu kita kena tahu dah nilai dia. So next X, the desired conversion was 0.2 kan. The final conversion dia nak adalah 20%, 0.2. So X 0.2. Then the minus RA adalah apabila X saya 0.2. So when my X is 0.2, if you see from the curve, when my X 0.2, 1 per minus RA is 3.33. So what you do, you straight away multiply with 3.33 sebab dia adalah 1 per minus RA apabila X saya 0.2, which is 3.33. So you multiply with 3.33, okay, you are left with only one unknown FA0. You can solve this, you will get your FA0 as 45.05 mole per second. So this question pun sebenarnya tak susah, tetapi you have to understand part yang kamu kena multiply, don't divide. Kalau table tu minus RA, kamu kena bahagi. Kalau plot is 1 per minus RA, you straight away multiply with the value. Then don't forget, you solve it correctly, you get your FA0 answer. So you have two different FA0. FA0 untuk CSTR, FA0 untuk PFR. It will be different because they are different reactor and they use different equation. So done for question number 3. So again, 1 or 2 minutes for you to do. If you are doing it, then I will come back in 1 to 2 minutes time. Okay, alright. So we are done for question number 3. Okay, we start with a quite easy one. We will go to the next question, question number 4. Okay, so question number 4 ni ada a little bit difficult. Okay, so this is question number 4. 3.5 mole per dm cube. Kejap saya besarkan balik. 3.5 mole per dm cube of pure A enters the reactor at the rate of 10 dm cube per second. Okay, at this part, kamu kena betul-betul be careful with the value that is given. Kamu kena betul-betul check value tu given tu sebenarnya apa. Sebab kalau part ni kamu dah buat salah, basically the entire thing calculation dah salah. Okay, first baca. Dia kata mole per dm cube. So kami ingat, mole per dm cube, dimension dia mole per volume. So mole per volume is concentration. So dia kata concentration. Dia kata A. So it's concentration of A. Then dia kata enters the reactor. So this is initial concentration of A. So this is CA0. So CA0 3.5. So let's say part ni kamu tersalah. Kami ingatkan 3.5 ni adalah FA0. If you put it as FA0, the entire calculation semua dah salah. Means at the very first step, kamu dah salah identify, kami ingatkan tu FA0, tapi sebenarnya adalah CA0. The entire question is zero ready for you. So make sure you cannot do this mistake. Tengok unit, kena pasti dulu apakah nilai itu. Okay, so this part, this is CA0. Next one, rate of 10 dm cube per second. So again, dm cube per second, dimension dia volume per time. So kamu tahu volume per time, volumetric flow rate. So dia kata this one initial, enters the reactor kan. So V0 10 dm cube per second. Epsilon, saya kena saya guna V0 dan epsilon sama tu volumetric flow rate V0 10 dm cube per second. So same concept, katakan kami ingat 10 ni adalah FA0. Whole question salah juga. Ataupun kami ingat 10 ni adalah CA0. Whole question salah juga. So you cannot do this mistake. Check unit, tengok dimension, kena pasti betul-betul. Okay, so done. Okay, so kita tahu CA0 3.5, V0 10. Okay, next dia kata using the data here, calculate reactor volume. So data yang diberi sekarang dalam bentuk table. Tadi dalam bentuk plot, now is in the form of table. So in the table dia beri kita X and minus RA. So kalau plot 1 per minus RA X, this one minus RA and X. Okay, so tu beza dia. Right, so let us go to the very first question. This so kita cari volume reactor, single CSTR conversion 80%. So dia nak kita cari volume CSTR, tadi disuruh kita cari FA0 bila dia beri volume. Soalan ni disuruh kita cari terus volume. So kalau kamu tak pasti nak start daripada mana, you can always start from the design equation first. Kamu tahu design equation dia, volume CSTR equals to FA0X per minus RA. So minus RA itu pada X yang kamu nak cari. Okay, so kamu nak tahu kan kalau kita nak cari volume, on the left hand side is our unknown yang we want to find. So the right hand side, all the three unknown, FA0, X, minus RA, kamu kena cari nilai dia. Kalau tak dapat ketiga-tiga nilai ni, kamu tak akan dapat volume CSTR. So first of all, FA0. So kamu perasan FA0 adalah molar flow rate. Dia mesti unit dia mesti, dimension dia mesti mole per time. So kalau kamu cek dalam soalan, tak ada sebarang nilai yang memberikan kita dimension mole per time. Sebab yang pertama, mole per volume. Yang kedua, volume per massa. Tapi kita tahu molar flow rate, dia mesti mole per time. So selagi kamu tak dapat FA0 yang ada dimension mole per time, you cannot solve this. Kamu tahu mesti jawapan kamu salah. So that's a way for you to already know. Kalau saya tak ada FA0 yang ada unit mole per time, mole per second ke, mole per hour ke, mole per day ke, selagi tak ada unit ni dalam nilai saya tak boleh buat. Salah. Okay. So then maybe you remember, tapi dia beri kita CA0 dan V0. So there is a correlation between FA0, CA0 and V0 because FA0 is equal to CA0 multiplied with V0. So you multiply your CA0, 3.5 mole per dm cube. You multiply with your volumetric flow rate, 10 dm cube per second. Okay, if you multiply correctly, you can see that I can cancel once more my unit of my volume. DMQ tu kamu tahu kan, kalau matematik atas bawah kita boleh cancel. We are left with mole per second. So betul lah, mole per second, mole per time. So you get already your FA0 first. So FA0 is 35 mole per second. So kalau kamu tengok soalan ni, dia tak suruh pun kamu cari FA0 sebenarnya. Tapi kamu tahu dalam formula, dalam equation saya tu, in the equation, I have FA0. So in order for me to solve it, I have to first find FA0. So that's part that you have to really understand dalam engineering question, especially now you're in semester yang dah advanced semester, dia takkan, soalan dah takkan straightforward kata, okay, cari FA0. Takkan. But you have to know by yourself, nak solve this, saya tak cukup lagi information, bagaimana saya nak dapatkan information tu dulu for me to finally solve the equation that I want. Okay, so that's one part that you have to really bear in mind when you're solving engineering question. So done on the FA0, the X is 0.8 lah, because the question say conversion 80%. So X is 0.8. So down minus RE. So minus RE is when my X, at my X that I want. So my X is 0.8. So dia adalah minus RA when my X is 0.8, which is 0.013. So kamu replace saja minus RA dengan 0.013. So tengok part ni kita bahagikan. Why we divide? Sebab table punya nilai adalah minus RA. So kamu kena bahagi dengan nilai minus RA itu. You will get the volume as 2153.85 dm cube. If you are not too sure, again, you can do the unit cancellation. I can cancel my mole. I can cancel my second. I'm left with dm cube. I want to find volume. I get dm cube. Dm cube is indeed volume. Most likely, your answer is correct. So done on the single CSDR. Okay, next. We go to PFR. So again, single PFR. So single PFR, kita kena cari juga dia punya volume. So volume of PFR equals to FA0 integrating 0 to 0.8. Why 0 to 0.8? Because one PFR, single PFR, converting from zero conversion to final conversion 0.8. Okay, dx per minus RA, convert into Simpson 1/3 rule, it becomes FA0 delta x per 3. Okay, so let's us discuss part ni. Sebab Simpson 1/3 rule, kamu kena ingat, kita kena divide x kita kan. So initial x kita 0, final x 0.8. Hence my middle x will be 0.4. So middle x tu kamu kena tahu sendiri macam nak cari titik tengah dia. 0, 0.8, middle x 0.4. Delta x is the gap or the julat or the difference between initial x to middle x. So initial x 0, middle x 0.4, delta x 0.4. Ataupun kamu nak cari kat belakang pun boleh. 0.4 to 0.8. The difference is also 0.4. So delta x 0.4 divided by 3. Okay, so done. 0.4 delta x 0.4 bagi dengan 3 sebab equation dia kata kena bahagi dengan 3. Third, the last 3 points. So it become 1 per minus RA at my initial x, which is 0, plus 4 per minus RA at my middle x, 0.4, plus 1 per minus RA at my final x, which is 0.8. So again, substitute je value, nak cari volume. So part yang kiri, apa yang kita nak cari. Part kanan semua kena ganti dengan nilai. So first part, FA0 masih 35 mole per second. Kita guna FA0 yang sama yang tadi kita kira untuk CSTR. Sebab FA0, dia tak bergantung kepada reaktor. Dia bergantung kepada, FA0 dalam soalan ni bergantung kepada CA0 dan V0. Kalau CA0 dan V0 tak berubah, of course my FA0 pun tak berubah. So that's why my FA0 still 35 mole per second. Okay, multiply with delta x 0.4 divided by 3. Okay, in the bracket, tengok table. When my x is 0, minus RA 0.053. When my x 0.4, minus RA 0.040. When my X 0.8 minus RA 0.013. So kamu replace saja dengan nilai. Don't forget, kamu kena divide by the value. You calculate correctly, you get the volume as 913.69 dm3. So this is the volume of a single PFR if we want to achieve conversion of 80%. So done for these two questions. Again, saya kecil sikit. I give you 1 minute to 2 minutes. Then I will proceed to part C and D. Sebab part C and D dah reactor in series. A little bit of a discussion. So you try to settle this. I will come back in 1 or 2 minutes. Right, okay, so done on question A and B. We go to the next two questions, C and D. Okay, so question C. Calculate the volume of the reactor. Calculate the volume of the reactors if two CSTR are connected in series with intermediate conversion 40%, final conversion 60%. Okay, sekarang soalan dah berubah sikit sebab sekarang saya ada dua reaktor. Reactor tu connected in series and first reactor dia achieve intermediate conversion 40%, 0.4 means X1 0.4. Means dalam reaktor pertama, dia convert daripada 0 to 0.4. X1 0.4. Dalam second reactor, final conversion 60%. X2 0.6. Means dalam reaktor kedua, dia convert daripada 0.4 kepada 0.6. X1 0.4, X2 0.6. They want us to find the volume. Okay, so kamu kena ingat, dua reaktor in series, kita kena cari two reactor volume. So we find for the first reactor, volume CSTR1 equals to, kalau kami ingat untuk reaktor pertama, the formula is similar to a single reactor. The only difference, dia menjadi FA0 X1. Kamu kena tulis X1, kamu tak boleh tulis X. Sebab kalau kamu tulis X, dalam soalan ni ada dua X, X1, X2. So you have to specify kalau reaktor pertama, dia adalah X1. Divided with minus RA at your X1. So FA0 dia masih sama sebab soalan tak ubah, doesn't change concentration, doesn't change your volumetric flow rate, your FA0 is still the same. Okay, so 35 mole per second. My X1 0.4, my minus RA when my X is 0.4, apabila X1 saya 0.4, minus RA dia adalah 0.040. How do I get that? Tengok ke atas table, when my x 0.4, my minus RA 0.040. So replace je 0.040, you get the volume as 350. So CSTR, first CSTR, normally memang student can do. The problem will come at the second CSTR sebab formula dah berubah. Part ni yang saya sentiasa kena emphasize. When you have reactor in series, formula untuk second CSTR tu dah kena modified. So it becomes F volume CSTR 2. Okay, kamu kena specify. Kamu mencari volume for the second CSTR equals to FA0. FA0 is there. In bracket become X2 minus X1. Don't forget this part. Dalam bracket dah menjadi X2 minus X1. Okay, so as I told you, exam regardless fizikal ke tak fizikal pun kamu memang tak payah hafal. Tapi kamu kena ingat, betul-betul ingat kalau reaktor kedua dalam sistem CSTR, dalam bracket tu dah menjadi X2 minus X1. Okay, divide dengan minus RA at your X2. Okay, empat ni pun kena selalu confuse. Minus RA ni bila X2 ke X1 sebab ada dua-dua X2, X1 kan. So don't forget, reaktor kedua minus RA dia pada X2. Reaktor pertama minus RA at X1. Okay, so replace je dengan nilai FA0 35, X2 0.6 as given in the question, X1 0.4. So as I told you, katakanlah kamu terconfuse. X1 tolak X2 atau X2 tolak X1. Kalau kamu buat X1 minus X2, you definitely get a negative value. So you know volume reactor can never be a negative. So itu logik dia. Nilai kamu kira negatif. Tapi kamu tahu volume reactor, volume vessel kan, volume vessel tak mungkin akan jadi negatif. Isi padu tak mungkin jadi negatif. So kamu dah tahu something is wrong. So switch je lah jadi X2 minus X1. So divide by minus RA when my X 0.6 at my X2 0.6. So tengok table balik. At 0.6 minus RA 0.025. So kamu replace je minus RA with 0.025. You divide, you calculate, you will get the volume as 280 dm cube. So soalan ni taklah susah, tetapi of course if you forget the equation y it become x2 minus x1, kamu lupa part tu, kamu just letak x2, which is normally what student do. Student akan letak FA0 x2. Yang tu biasanya student akan buat. So tu yang menyebabkan dia salah. Kalau reaktor kedua mesti x2 minus x1. Okay, so done on part C. We go to part D. So part D pula sekarang adalah 2 PFR connected in series with intermediate conversion 60%. So final conversion 80%. So sekarang soalan D, saya ada 2 PFR, my X1 0.6, my X2 0.8. Okay, so kita nak cari volume PFR, X1 0.6, X2 0.8. Okay, so let us go one by one. So in the first PFR, volume of the first PFR equals to FA0 integrating from 0 to 0.6. Why 0 to 0.6? Sebab in the first PFR, I go from zero conversion, nothing is converted until 60% dalam reaktor pertama. Sebab tu lower limit kosong, upper limit 0.6 dx per minus RE. Why I always emphasize on lower limit, upper limit? Sebab nanti bila kita nak buat pengiraan Simpson one-third rule tu, kamu dah akan tahu starting point dengan final point dia. That's why it become FA0 delta X per 3. Okay, so this part kita kira berapa delta X. So again, inertia X 0, our lower limit, our upper limit was 0.6. So 0 to 0.6, middle X dia adalah 0.3. So middle X tu kamu kena tahu sendiri macam nak cari. It's just a middle conversion between 0 to 0.6. So middle X dia 0.3. Then you can find your delta X. So delta X will be from 0 to 0.3, delta X dia, beza dia 0.3. Kalau kat belakang pun 0.3 to 0.6, the middle X is still 0.3. The gap, the delta X, the difference is still 0.3. So delta X is 0.3. Divide by 3. Okay. In bracket, 1 per minus RA at my lower limit, which is X0. So 1 per minus RA where my X0. Plus 4 per minus RA at my middle X, which is 0.3. So 4 over minus RA when my X 0.3 plus 1 per minus RA at my upper X, upper limit, which is 0.6. So 1 per minus RA when my X 0.6. When you have all these three, you replace into the equation. So FA naught 35, delta X 0.3 divided by 3. Find from the table at 0.6 minus RA dia 0.053. At 0 minus RA 0.053. At 0.3 minus RA 0.045. At 0.6 minus RA 0.025. You calculate these, you will get ultimately the volume as 517.15 dm cube. Okay, so that's the final answer for the volume of first PFR. So similar concept, first PFR, normally student tak buat salah sebab first PFR ni sama macam single PFR sebenarnya. Problem only comes at the second reactor. Always the problem comes at the second reactor sebab, okay, now let us calculate second reactor. Volume PFR2, the second reactor volume equals to FA naught, masih ada, but now integrating from 0.6 to 0.8. So kenapa daripada 0.6 to 0.8? Sebab dalam reaktor kedua, dia convert yang asal yang masuk adalah 0.6. Dia convert kepada final conversion dia 0.8. X1 0.6, X2 0.8. So it become 0.6, 0.8 dx per minus RE. So then ganti dalam bentuk Simpson-Wanted rule, FA naught delta X per 3. Delta X ni again, this part yang selalu student akan make the mistake. Now you have to understand, lower limit 0.6, upper limit 0.8. So maknanya X1 0.6, X2 0.8, middle X di antara 0.6 and 0.8, titik tengah dia, X dia adalah 0.7. Okay, so delta X dia, the gap or the difference is from 0.6 to 0.7, gap dia adalah 0.1. Kalau belakang pun 0.7 to 0.8, the delta X is also 0.1, the difference. That's why delta X is 0.1. This part memang always student will make the mistake bila nak cari delta X. Part ni yang selalu student akan buat salah. Sebab tu I have to keep repeating it. It's the gap between initial X to the middle X or middle X to the final X. So you have to be very careful about this part. So dah ganti delta X, okay, 0.1 divided by 3. FA naught kita dah tahu. Then go to the 3 point. So 3 point ni pun kamu kena be very careful because now your initial X is X1, 0.6. So that's why it become 1 per minus RA when my X 0.6 plus 4 per minus RA when my X at 0.7 and my middle X plus 1 per minus RA and my final X 0.8. So you get these 3 points correctly, then you just look from the table for the 3 values. So tengok table pada 0.6 berapa minus RA, pada 0.7 how much is minus RA, at 0.8 how much is your minus RA. You replace the number accurately, accordingly you should be able to get the volume of the PFR for the second one as 395.67 dm cube. So similar to CSTR, part yang student tend to do mistake, part delta X. Dan part yang 3 point tu dia tak sure, dia kena start dengan X1. X1, last point X2, middle X2 dia kena cari sini. Dia kena tahu titik tengah antara X1 dan X2. Okay. So done for question number 4. Question number 4 kan? Okay. So again, as usual, I give you about 1 to 2 minute break. Okay. Not break, gap or time so that you can try to attempt it. Then I will come back again in 1 to 2 minutes time. Right. Okay, alright. So we continue with the next question. So we go to question number 5. So answer number 5, we come back to question with Levens-Sphere plot. Kejap saya tengok soalan 6. Okay, let's go to question with Levens-Sphere plot. Right. So the question says, the gas phase reaction is given as follows. A produce B. Okay, the irreversible reaction is carried out isothermally in a flow reactor at the initial rate of 10 dm cube per second. Okay, so this is at this part, okay, there are certain words that mungkin kamu tak pasti lagi, tapi saya explainkan dulu. So first thing first, dia adalah gas phase reaction. One. Second, dia kata irreversible reaction. So until chapter 4, we will still discuss irreversible reaction, meaning reaction that occurs at forward direction. But nanti dalam chapter 4, you will also learn reversible reaction. So reversible means it goes forward, it can also goes backward. Okay, next, isothermally. So nanti sampai chapter 6, you will learn first isothermal je. Means there's no changes of temperature during the reaction. But later dalam chapter 6, you will then learn for the system di mana we have change of temperature. Okay, so that one so far okay. Next, dia kata flow reactor. Dia kata initial rate 10 dm cube per second. Okay, so dia kata dm cube per second. So you know dm cube volume, second time, volume per time, volumetric flow rate. So dia kata initial, right? So this is epsilon naught of V naught. V naught equals to 10 dm cube per second. Saya satu you katakan part ni kamu tersalah, kami ingatkan yang 10 ni adalah CA naught. Habislah keseluruhan soalan. Ataupun kami ingat 10 ni adalah FA naught. Habislah keseluruhan soalan. So you have to be very careful. This is initial volumetric flow rate, V naught 10. Okay, kadang-kadang saya guna V naught, kadang saya guna epsilon naught. Sama dia maksudnya volumetric flow rate. Okay. The feed mixture consists of 45 mole % inert and the balanced reactant A at 40 Celsius. So can you see this part? Dia beritahu kita initially tu feed tu initial lah kan, consists of 45 mole % inert balanced A. So kamu perasan dalam in my reaction I have one reactant which is A. However, this is gas phase kan, this is gas A. However, it's not 100% gas A dalam sistem pada waktu asal, or in the feed it wasn't 100% pure gas A. Instead, we have 45 mole % of inert gas. Kita tak tahulah gas tu apa, tapi it's inert gas, meaning it won't be involved in the reaction, but it exists in the system. So 45 mole % gas inert. So kalau balance dia A means 55 mole % tu gas A. So 45 mole % inert, baki 55% mole tu adalah gas A. Means YA0 saya 55 YA0 saya 0.55. Okay, kenapa 0.55? Sebab 45% inert, 55% A. So YA0 0.55. Next, dia beritahu kita temperature 40 Celsius, T naught 40 Celsius. The initial partial pressure of the inert is 5 atm. So dia beri kita pula partial pressure inert. So dia beritahu kita tekanan inert tu adalah 5 atm. So now information dia beritahu kita, dia tell us I have 45% inert and this 45% inert ni adalah 5 atm. Dia bukan total, dia bukan gas A, bukan campuran gas A, gas B, but bukan campuran gas A and inert. It's just the inert gas. Yang 45% inert gas ni, pressure dia 5 atm. Okay, that's information they give us. Right. So this says they give us the Levens-Sphere plot. Okay. Right. So Levens-Sphere plot 1 per minus RA versus X. Right. Next. The reaction was conducted in 2 CSTR in series. Determine the volume of both reactors required to achieve 60% conversion at the first reactor and 80% conversion at the second reactor. Dia kata kita run this in a CSTR. Dia nak kita cari volume, okay, and they say X1 0.6, X2 0.8. They want us to find the volume. Okay, so let's say you don't know where to start. Of course lah, kita nak cari volume. Kita start dulu dengan design equation dia. Okay, so kalau kamu confuse part-part sentence yang banyak-banyak information tu, why all sudden, kenapa all sudden ramai yang left kan? Kamu ada kelas lain ke? Hello, do you have any other class? Because all sudden I realize 10 to 20, 10 student terus leave. Do you have any other class selepas ni ke? Ada yang boleh jawabkan ke? Tak sure.
Tak sure.
Saya punya 11:30.
Sebab memang ni waktu lab.
Our internet tiba-tiba suddenly disconnected.
Oh, alright. No wonder. I tengok tiba-tiba 10-20 orang tinggal. Okay, then we tunggu dulu. I wait for the rest to come back. Kita tunggu kejap Right, so I will continue. Alright, I'll continue back. Okay, I think some of you already come back. But tak apa, kalau yang terlepas tu nanti just watch the video back. Right, so in this question, dia nak cari volume. So of course, if you are not too sure, information macam banyak sangat kan, kamu tak sure nak start pada mana, you just start from the design equation. Sebab kamu tahu nak cari volume, dia mesti start dengan design equation. Okay, so you know, to find the volume, you will start for the first reactor, for the first CSTR, the equation is given as volume CSTR1 equals to FA0X per minus RA at X1. Okay, you start from there. Okay, so you know, kalau kita nak cari volume reactor, because the question wants us to find the volume. So the left hand side is the one that I want to find. So on the right hand side, every unknown tu kamu dah kena cari dulu nilai. Kalau tak ada nilai memang tak boleh solve. So first, kita start dengan FA0. So same concept. Kalau nak tahu, nak cari FA0, dia mestilah that value is in the form of mole per time. So kalau kamu perasan dalam soalan, there's no information yang berikan kamu mole per time. Yang ada pun hanya volume per time, which is volumetric flow rate. Okay. However, it can give you a little bit of indicator. Sebab kamu tahu kan, kalau kita nak cari FA0, kita boleh cari kalau kita tahu V0 dan CA0. Previous question we already know, right? FA0 equals to CA0 multiply with V0. Means kalau saya tahu CA0, saya tahu V0. By right, saya boleh cari FA0. So that's your first indicator. Okay. Second, kamu tahu pula V0 dah diberi. We already know V0. Okay, means if I know CA0, by right, I can already get my FE0. So the challenge pula CA0. Sebab kamu tengok dalam soalan, tak ada pun sebarang nilai dalam bentuk mole per volume. Sebab concentration mesti mole per volume. There was nothing in the question in the form of mole per volume. However, kamu ingat pula, sebab tu dia kata soalan engineering, dia ada step where you have to actually think from step to step. Dia tak beritahu kamu directly kamu kena cari FA0. Dia tak beritahu kamu directly kamu kena cari ni. Tapi kamu kena fikir how to actually solve it. Okay, now next, cabaran dia nak tahu FA0, kena cari CA0. Okay, CA0 tak diberi. However, you know this is gas phase reaction. Kalau gas phase, and kalau kamu tengok dalam soalan, dia beri suhu, dia beri tekanan. Regardless apalah tekanan atau suhu tu, it tells you that most likely you can use the ideal gas law. Sebab ideal gas law boleh cari CA0. So CA0 darab V0, dapatlah FA0. Dapat FA0, bolehlah solve. Okay, so kamu tahu step yang kedua sekarang ataupun step ketiga, kita nak kena cari CA0 dulu. Dapat CA0, darab V0, dapat FA0, boleh solve problem. But how to find CA0 pula? Okay, so CA0 equals dengan, sama je konsep, sama dengan YA0 P0 per RT0. Okay, as I told you, tekanan tu nak cari untuk A, dia mesti kepekatan A, that pressure must be from A. Kalau dia beri kita total pressure multiply dengan mole fraction A. Kalau dia beri kita terus pressure A, terus guna pressure A divide by RT0. Okay. So soalan part ni pula, dia beri kita, they do give us YA0 sebab dia kan dia kata 45 mole percent inert. Remainder A. So YA0 0.55. Okay, done. 0.55 tu kita dah tahu. Mole fraction for A is 55%, 0.55. What about P0? Total pressure dalam sistem. So kalau kamu perasan dalam soalan ni, dia beri kita pressure, but that pressure was partial pressure of the inert. Kita nak cari sebenarnya tekanan A, tapi dia tak beri kita tekanan A tau, dia beri kita tekanan inert. So macam mana kita nak cari, kita ada dua option. Dia beri kita tekanan A kan, tekanan inert. Either kamu nak cari jumlah tekanan darab dengan mole fraction ataupun kamu juga boleh cari tekanan A. Which are the option? Actually, both pun kamu boleh buat. Okay, what do I mean by that? Okay. In this example, saya guna Raoult's law untuk cari jumlah tekanan. Okay, cara dia nak cari jumlah tekanan adalah guna Raoult's law. Means, kalau saya tahu mole fraction inert, saya multiply dengan total pressure, saya dapat pressure inert. So, saya dah tahu pressure inert kan? Saya dah tahu pressure inert, saya tahu mole fraction inert, saya boleh tahu total pressure. Atau erti kata yang saya senang nak terangkan, okay, because this is official calculation, I show you this way. In easier way to understand, macam ni. 45% mole percent inert ni bersamaan dengan 5 ATM. 45% ni bersamaan dengan 5 ATM. Kalau kamu nak tahu jumlah tekanan keseluruhan sistem P0 bersamaan dengan 100%. 45% sama dengan 5 ATM. Kalau 100% berapa ATM? Kalau kamu ingat darab silang, kamu berdarab silang kan? Bila kamu darab silang, kamu sebenarnya akan dapat total pressure tu 11.11. If you use that way, which is as shown here. Okay, menggunakan cara yang sama ni. 45%, 5 ATM. 100%, how many ATM? 11.11. This is the total pressure of the system. Means pressure A tambah pressure inert. So kalau nak tahu pressure A, kamu kena darablah dengan 0.55. That's one way. Another way, kalau kamu nak terus tahu directly pressure A pun boleh. PA0. Macam nak tahu? Darab silang lagi. 45% inert sama dengan 5 ATM. Kalau saya ada 55% A, berapa ATM? Darab silang je. So means 0.55 times 5 divided by 0.45, you get terus pressure A. That's also another way. Kalau kamu terus dapat pressure A, kamu terus ganti dengan PA0 tu. Kamu dah jangan darab dengan 0.55. So that's why I say in engineering, especially reaction engineering, kadang-kadang few student will have different way of doing the calculation. Dia ada yang macam I told you just now, some will find P0, some will find PA0. Sama je jawapan akhir dia. But make sure you use it correctly. Macam saya, in this question, I find first total pressure. So, I mesti darab dengan 0.55. Kalau kamu terus cari pressure A, dah tak payah darab. Terus guna pressure tu. Okay, so darab 0.55 divide by RT0. So, my pressure ATM, I use lah gas constant yang ada ATM. So 0.082 ATM dN cube per mole Kelvin. Temperature, my T0 was 40 Celsius. I convert into Kelvin. I will get my initial concentration 0.238 mole per dm cube. So you convert the unit, you get the concentration. But jangan stop kat sana, tak habis lagi soalan, tak solve pun lagi soalan sebab kita sebenarnya nak cari apa? FA0. So dah tahu CA0, okay, multiply with the given volumetric flow rate which is 10, then only you get your FA0. So jalan-jalan panjang-panjang ni sebenarnya kamu nak cari FA0 je dulu, belum pun lagi solve. Dah dapat FA0, baru kamu boleh solve soalan itu. Then only you can replace your FA0. You can replace your X1 which is 0.6. Then you have to find from the plot when my X 0.6, 1 per minus RA 8.85. So you multiply with 8.85. Jangan lupa kalau guna plot, dia terus darab sebab plot tu adalah 1 per minus RA pada X yang kamu nak cari. So it was 8.85, you multiply, you get the volume of your CSTR1 as 12.64. So done for question part reactor pertama. Second reactor. So second reactor, volume CSTR2 equals to formula, jangan lupa second reactor, FA0 equals to FA0 in bracket X2 minus X1, tutup bracket, divided by minus RA at my X2. So X2 0.6, X1 X2 0.8, X1 0.6, minus RA is when my X is 0.8, minus RA pada X2. So when my X 0.8, my 1 per minus RA is 20 from the plot. Okay, daripada plot kamu dah tahu nilai dia. Kamu ganti sahaja. So become FA0. FA0 masih sama as again. Kalau tak ada perubahan volumetric flow rate, there are no changes in temperature, pressure, so on and so forth. FA0 tu masih sama. You can still use the same FA0. So FA0 multiply with X2 minus X1 multiply with 1 per minus RA when my X 0.8. You get the volume as 9.52. Done for first part of the question. So question ni dia not I would say a bit tricky part yang nak cari CA0 tu, ataupun kamu kena tahu sebenarnya kita nak guna FA0 dalam equation. FA0 tak diberi, tapi kita tahu FA0 boleh dicari kalau kita tahu CA0 dan V0. Tapi CA0 tak diberi, kamu kena cari CA0. Tapi CA0 pun tak diberi information straightforward. So that's what I keep emphasizing. You have to really understand question. Sebab dalam test exam saya tak akan bagi pun sebiji macam ni. I will change a little bit. But kalau kamu faham, you can answer. But if you don't understand, like kamu just ikut je jalan kerja ni, then it will be a little bit problem later as you solve question. Okay? So want to meet? Yes.
I nak tengok volume untuk CSTR1 boleh tak?
Here. Tak sama ke jawapan? 12.64. Betul ke? Do you get the same answer? Siapa tadi tanya saya tu? Dapat tak jawapan yang sama?
I tengah cari, I tak dapat tapi macam
FA0 kamu 2.38 from here. X1 0.6. At 0.6 my 1 per minus RA 8.85. 8.85 ni. So darab dengan 8.85.
Oh darab
Sebab ni kan 1 per minus RA, jangan lupa. Jangan lupa. Dia bukan minus RA, ni adalah 1 per minus RA. So terus darab, tak boleh bagi. Ingat tak? Kalau table, kalau tadi kita guna table, tu adalah minus RA. Kamu kena bahagi dengan nilai tu. Dalam plot, dia adalah 1 per minus RA. Dia terus nilai 1 per minus RA itu. So kamu terus darab je dengan nilai tu. Kamu tak boleh bagi. Faham tak?
Faham. Take note lah.
You must really take note. That's why saya emphasize few times lah. Jangan lupa beza bila tengok plot dengan bila ambil daripada table. Ambil daripada table kena bagi. Ambil daripada plot darab terus. Okay? Right. So then I go to the next part of the question. Okay, next part. Okay, part ni dah susah sikit. Okay, this part is slightly different already the question. Or this one kamu cari FA0, kamu cari volume. Soalan ni dikata, let's see the question. The question says, reaction conducted in 2 PFR in series, determine the space-time. Kamu baru belajar semalam kan, space-time, tau. For both reactor to achieve 40% intermediate conversion and overall conversion 80%. Okay, soalan ni kata saya ada 2 PFR in series. Reaktor pertama X1 0.4, reaktor kedua X2 0.8. And dia kata sekarang dia bukan suruh cari volume, dia bukan suruh cari FA0, dia suruh kita cari space time. So space time sekarang kamu dah pernah belajar, saya dah ajar space time. Tapi saya tak ajar space time in the form of design reactor volume kan, but this question involve both. So how do we do it? Okay, so now mind. Katakan kamu tak sure, again, kamu start je dengan design equation. Sebab kalau melibatkan Lemonsphere plot, the table, definitely it will start first from the design equation. So let us start from the design equation. Design equation untuk PFR. Volume PFR 1 equals to, sebab dua reaktor in volume, dua reaktor in series. Okay, so reactor 1, reactor 2. Okay, so volume reactor 1 equals to FA0. Integrating 0 to 0.4 sebab reaktor pertama achieve X1 0.4 dx per minus RE. Ni yang kamu tahu yang design equation. Okay. However, kalau kamu ingat, okay, space time semalam saya ajar kamu, space time tau equals to volume reactor over initial volumetric flow rate, V0. V per V0 or V per epsilon naught. V besar tu volume, epsilon naught tu volumetric flow rate. Baru kita dapat kita punya tau. Okay. So kalau kamu perasan, kalau kita nak cari tau, means dalam equation saya dah kena ada volume dan volumetric flow rate. Selagi tak ada volume, tak ada initial volumetric flow rate, tak mungkin saya akan tahu tau. Okay. So if you check this first part of the equation, part yang depan, volume tu kita dah ada. Okay, saya nak cari tau, saya tahu kena ada volumetric flow rate, initial volumetric flow rate. Volume saya dah ada, tapi initial volumetric flow rate saya tak ada lagi. Tetapi kamu pernah ingat, molar flow rate FA0 ni kan sama dengan CA0 multiply with V0. Okay, so part ni yang kena sikit lah, kamu kena faham sikit. Okay. Kamu ingat, okay, FA0 tu boleh juga kita we put it in the form of CA0 multiply with V0. Okay, so when I do that, so become CA0 V0, integral part masih sama, 0 to 0.4 dx per minus RE. So when I do this, what happens? Saya nak space time kan? So if you realize, I can move my V0 sekarang kat bahagian kanan kan. If I move my V0, my initial volumetric flow rate, from right to left to here, it become a division. So it become volume PFR 1 divide with initial volumetric flow rate. So do you realize kalau volume bahagi dengan initial volumetric flow rate, dapatlah space time untuk reaktor pertama saya. Kalau saya divide volume reaktor pertama dengan initial volumetric flow rate, saya dapatlah space time untuk reaktor pertama saya. So left hand side saya dah dapat apa yang saya nak, which is my space time. What happens to my right hand side? Right hand side, saya kan dah move my V0, volumetric flow rate saya dah move ke bahagian kiri. So bahagian kanan saya hanya tinggal dengan CA0. V0 dah tak ada, V0 dah dipindah ke belah kiri. So become CA0, integral part masih sama. So become 0, 0.4 dx per minus RE. So again, kita kena tukar dalam bentuk Simpson one-third rule. So CA0 tu kekal sebab CA0 tu tak ada kaitan dengan Simpson one-third rule. Simpson one-third rule is to address the integral part. So bahagian depan CA0 tinggal, bahagian belakang integral dah menjadi Simpson one-third rule. So now I can already find directly my space-time. Space-time sama dengan CA0 ganti dengan Simpson one-third rule. Yang Simpson one-third rule punya pengiraan tu adalah masih sama. Meaning, first of all, CA0 kita guna yang asal part A yang tadi kita cari CA0 yang tadi tu kita masih boleh guna sebab tak ada perubahan tekanan, suhu, so on. The CA0 is still the same, 0.238. Delta X, okay, as I told you, dia daripada 0 to 0.4. X1 kita 0.4, right? 0 to 0.4, our middle X is 0.2. Our gap, delta X will be 0 to 0.2, delta X is 0.2. 0.2 to 0.4, delta X is also 0.2. So delta X 0.2 divided by 3. Then in the bracket, 1 per minus RA at my X0 plus 4 per minus RA at my middle X 0.2 plus 1 per minus RA when my X 0.4. So again, jangan lupa kamu menggunakan plot. Menggunakan plot, dia adalah nilai tu kamu kena take directly. You have to substitute directly. You have to multiply directly dan bukan bahagi sebab nilai plot adalah 1 per minus RA. Dia bukan minus RA. Dia adalah 1 per minus RA. Kamu terus darab directly this value. So you do it correctly, you get space time dia sebagai 0.33 second. In your first reactor, the space time is 0.33 second. So that's for the first reactor. Untuk second reactor, space time pun dah berlainan. Kenapa? Sebab space time reaktor pertama adalah sama dengan volume reaktor pertama bahagi initial volumetric flow rate. Space time yang kedua sama dengan volume reaktor kedua divide by the initial volumetric flow rate. Your volume reactor takkan sama dah. Kalau volume takkan sama, space time pun takkan sama. So you have to find the second space time. So apa beza dia? So become sama je konsep dia, volume PFR2, kita start daripada equation yang sama, volume PFR2 equals to FA0, ini equation design yang original, integrating 0.4 to 0.8 sebab reaktor kedua is integrating from X1 to X2, 0.4 to 0.8 dx per minus RA. Same concept, saya nak cari space time, saya kena ada volume per initial volumetric flow rate. Volume saya dah ada, saya tak ada volumetric flow rate, initial volumetric flow rate. But I remember FA0 is equal to CA0 multiplied with V0. Itu adalah perkataan yang kita dah pernah tahu. Okay, so I replace it that way. Then integral part masih sama. Part integral ni kita tak kacau, kita biarkan sahaja. Then next part, I will again move my initial volumetric flow rate from right to left. So kamu ingat mathematics kan, kalau kamu pindah daripada kiri ke kanan, yang pengatas akan jadi pengbawah. Dia akan become a division. Sebab tu dia menjadi volume PFR2 divide by the initial volumetric flow rate. So it become a division. So volume bahagi dengan volumetric flow rate, dapatlah space time for the second reactor. That's how we express now the equation. Now it become space time untuk reaktor kedua. So kalau kamu perasan memang dalam note saya memang tak ajar part ni. Tapi saya ajar part ni separately sebenarnya. So dalam tutorial ni kita combine that knowledge. So that's what you have to understand about reaction. Kamu kena somewhat know equation ataupun somewhat know perkaitan equation, and you have to learn how to sometimes rearrange or recombine equation untuk mendapat apa yang kamu nak cari. Okay. So then equals to on your right hand side become CA dot, sebab V0 dah tak ada, V0 dah kena pindah kan, tinggal CA0, dan your integral part. Integral jangan lupa X1 to X2. So in terms of Simpson wanted rule, CA0 maintains, integral part become delta X per 3. So again sama, kita start dengan 0.4, we end with 0.8. So the middle X will be 0.6. So the difference of X from 0.4 to 0.6, dia punya difference 0.2. From 0.6 to 0.8, difference dia pun masih 0.2. So delta X is 0.2 divide by 3. CA0 masih sama, kita tak ubah pressure, tak ubah temperature. CA0 is still the same. So at the back, become 3 points, right? So 1 per minus RA when my X 0.4 plus 4 per minus RA when my X 0.6 plus 1 per minus RA when my X 0.8. So look from the plot, make sure again tengok betul-betul daripada plot, dia adalah 1 per minus RA, kamu terus multiply directly the answer, okay? Don't forget, multiply correctly, you get the space time for the second reactor as 0.96 second. That's the space time for your second reactor for this PFR. Okay, so done for this question. I will give you about 1 minute. Okay, but I will end the tutorial. Actually, I will end this tutorial at this question sebab I don't think you can go anymore. Soalan dah sampai 5 soalan. Okay, so I will continue next week. I will continue this tutorial next week sebab we still got time. So I give you 1 to 2 minutes first. Then after that, I will end the tutorial and I will see you next Monday for the lecture. Okay, alright. So kamu tengok dulu kejap. Nanti saya akan tutup. a homework for you, extra work, because I would like you to try to attempt by yourself the question number 7 for you to test whether do you understand or not the tutorial. Okay, if you can do question number 7 by yourself, the answers are already given in the question itself. I already give you the final answer. You are able to solve it by yourself. That probably means that you are okay already for chapter 2. Okay, so I will just discuss one question for chapter 2 tutorial. Okay, so for question number 6, alright, we have, saya buka yang besar. We have a mixture consists of pure A enters the reactor. Okay, so whenever you see the word pure, okay, pure A, you know it means it's 100% of A that enters initially. So that implies that there's only one reactant, and the second implication, it means there are no other system or there are no other compounds in the system initially except for A. Okay, so maksudnya kalau in terms of mole percent, 100% mole A, ataupun dalam terms fraction, YA0 is actually 1. Okay, so that one is extra information, extra knowledge for you. Kalau dia kata pure A enters the reactor initially, dia ada dua implication. First implication is only one reactant, reactant A. Second implication means initially 100 mole percent A, which is YA0, the mole fraction. Initial mole fraction of A is 1. Okay, so they give us the form of a table. So ingatkan table ni, kalau kamu perasan, kamu last Monday we already do chapter 3, right? So chapter 3 tu kalau kamu perasan, we are learning how to calculate minus RA. So dalam chapter 2, minus RA itu dah diberi kepada kamu dalam bentuk table. Meaning if I have X, I give you the minus RA. So we use this table to calculate. So dalam chapter 3 yang kamu belajar last Monday tu, kita tak tahu minus RA tu. Sebab tu kita macam reverse engineering. Kita kena kira pula minus RA for that case, right? Okay, so in the plant, there are available 250 dm³ CSTR reactors or 250 dm³ PFR reactors. Okay, so imagine in your plant, you have the two types of reactor. You have CSTR, of which kamu ada dua CSTR dengan volume dia 50 dm³. So kamu tengok dm³, dimension dia volume, kamu tahu dia adalah volume reactor kamu. So you have two CSTR, each 50 dm³, and you have two PFR, each also 50 dm³ the volume. So basically you have 4 reactors. 2 CSTR, 2 PFR, 4 reactor pun volume dia 50 dm³. Okay. To achieve higher overall conversion of A, the technologists decided to use either one of the reactor in series. Okay, so dia kata untuk mencapai conversion yang lebih tinggi, okay, the technologists decided dia kena guna either dua reactor, dua CSTR atau dua PFR, dan yang kedua reactors ni mesti bersambung secara series. Okay. It is targeted that intermediate conversion to be achieved 20%. Okay, kamu tahu kan intermediate conversion dengan overall conversion, dan intermediate conversion in the reactor before the final reactor. Overall conversion mesti conversion pada final reactor. So meaning in this case we got 2 CSTR atau 2 PFR. So the conversion in the first reactors. So the first CSTR atau first PFR dia lah X1 dia 0.2. So kamu assume ada kamu guna PFR yang bersiri atau CSTR yang bersiri, reaktor pertama tu conversion yang dicapai mestilah 0.2. X1 0.2 and overall conversion 80%. So means conversion at the second reactor, either second CSTR ke, second PFR ke, X2 dia adalah 0.8. Okay, so either one system pun, the conversion in the second reactor must be 0.8. So this is initial flow rate 1.5 mole per second. Okay, so you know initial means dia adalah molar flow rate yang dia adalah the value at the initial. Okay, then dikata mole per second, 1.5 mole per second. So now you dah tahu, right? Mole, dimension dia pun mole. Second dimension dia time. So mole per time, molar flow rate. So molar flow rate kamu tahu is F, right? So initial not. Then kalau initial yang reactant masuk hanyalah A. So is FA0. So they give you already FA0 1.5 mole per second. So imagine, like I always keep reminding you, when you see the number, be very careful. Contohnya katakan 1.5 ni, kamu tersalah. Okay, it's actually FA0 kan, tapi katakan kamu ingat dia CA0. So if you put it wrongly, memang the whole entire calculation akan jadi salah. So that's the tendency yang biasa macam students cannot do well in reaction. It's basically normally is this reason. Dia tersalah tengok value, tersalah identify value tu adalah sebenarnya apa. Sebab dalam soalan dia tak tuliskan molar flow rate kan, ditulis flow rate. So kamu boleh assume molar flow rate, dia boleh jadi volumetric flow rate juga sebenarnya. So you have to be very careful about the value and the unit. So in this case, this is FA0. Okay, dia kata evaluate which reactor configuration can be used to achieve the targeted conversion by comparing the calculated and available reactor volume. State the reason. Okay, so dia tanya sekarang, since we have two configuration, okay, kamu bayangkan dalam lab kamu punya plant, you have two configuration. Either you want to use 2 CSTR or you want to use 2 PFR. Tapi syarat dia, volume tu dah ada, volume tu dah available, and conversion tu mesti mencapai apa yang dia nak, 0.2 X1, 0.8 for X2. So dia tanya, kita kena evaluate reaktor, susunan reaktor PFR ke atau CSTR ataupun kedua-dua yang kita boleh guna untuk memenuhi to fulfill the conversion requirement. So how do we do this? So actually this question is example of problem solving. You know, all this one, kamu cari volume, which is katakanlah in your plan you have the budget or you are given the freedom to purchase new reactor. Okay, kamu cari volume, kamu purchase lah reactor volume yang memenuhi apa yang kamu nak. Tapi most of the time dalam plant, that's very rarely you are able to purchase new equipment unless your plant is really a new plant. If your plant has already been established, very rarely you are allowed to purchase new equipment. Most of the time you have to make do with what you have. So kamu macam problem solving lah. Okay, saya dah ada equipment ni, boleh tak saya guna equipment yang sedia ada kalau saya masih nak memenuhi certain requirement. So how do we solve this? Okay, so to solve this problem is basically what you do is, that's why dia kata compare calculated and available reactor volume. Means katakan you know your requirement of the conversion, you calculate the volume reactor yang diperlukan. When you calculate the volume, that's actually the minimum volume of your reactor required for you to achieve that conversion. So when you calculate the volume, you compare dengan the available reactor volume. So maksudnya, katakan if you calculate the reactor volume is smaller or lesser than the available volume, then you can use the reactor. Tetapi katakan apa yang kamu kira tu, volume yang kamu kira tu adalah lebih besar daripada volume reactor yang sedia ada, hence you cannot use the reactor. Sebab apa yang kamu kira tu adalah volume minimum ataupun volume yang paling kecil yang diperlukan untuk kamu achieve the desired conversion. So example, let's say you calculate the volume reactor yang kamu perlukan adalah 5 liter. Means kalau kamu tak ada volume reactor 5 liter ni, tindak balas ni tak boleh berlaku untuk mencapai conversion yang kamu nak. So you calculate 5 liter. Let's say in your plant, the reactor yang ada hanyalah 3 liter. So definitely you cannot run already because the 3 liter reactor yang ada kat plant tu takkan dapat mencapai conversion yang kamu kira. However, let's say you calculate 5 liter, kat dalam plant kamu tu reaktor tu adalah katakan 7 liter. So then yes, the available reactor can be used for the system. Okay, so that's the meaning of this. Tetapi in this case, kamu kena berhati-hati. It's not only one reactor. You have 2 reactor in series. Meaning, you have to make sure both reactor tu memenuhi is lesser than the available reactor volume. Tak boleh salah satu saja. Sebab kalau salah satu pun, tindak balas tu masih takkan dapat mencapai conversion, kedua-dua conversion yang dikendaki. Because you remember, conversion tak reset. First reactor flows to the second reactor. Means both reactor volume tu yang available mestilah cukup for both reaction as well. So means, what do we do? Kita kira dulu volume CSTR1, CSTR2, we compare with the available plant punya reactor, we calculate PFR1, PFR2, kita compare lagi sekali dengan volume PFR yang available in the plant. Okay, so we always start first with CSTR lah. CSTR is the easiest calculation. Okay, so now we calculate. The first CSTR, volume first CSTR, if you forget, okay, don't worry, as I told you, it's an open book. You can always refer to the notes. Okay, so the formula is volume CSTR1 equals to FA0 X1 per minus RA at your X1 or at your intermediate conversion. Okay, so your FA0 is 1.5 mole per second. We have already identified from the question. X1 is a 0.2, your conversion at the first reactor, intermediate conversion, divided by minus RA at X1, sorry, maksudnya minus RA when your X is 0.2. So you look at the table, senang je tengok table, when my X 0.2, minus RA dia 0.050. Okay, so sebab tu chapter 2 ni senang. Kamu dah tak payah kira minus RA, dia terus bagi je. Kamu tahu conversion, kamu terus tahu dah berapa minus RA dia, which is 0.050. Okay, so when you calculate, the volume of the first CSTR is actually 6 dm cube. Means, kata lain, kamu perlukan sekurang-kurangnya 6 dm cube volume reactor tu, kamu dah boleh mencapai conversion 0.2 ataupun 20%. Okay, done. So we go to the next one. So for the second reactor, kita nak kira untuk reaktor kedua sebab reaktor CSTR tu is connected by series. So the volume in the second reactor, VCSTR2, okay, is equal to FA0. Now equation dia dah berubah. Kamu kena ingat part ni. Biasa macam first reactor, student takkan buat salah. Usually, rarely they do mistakes in the first reactor, but they will tend to do mistakes in the second reactor sebab dia lupa kalau reaktor kedua, volume dia equals to FA0. In bracket tu ada X2 minus X1. Okay, kita dah belajar kan dalam chapter 2 how to derive the equation. Don't forget kalau reaktor kedua, reaktor ketiga, reaktor keempat, reaktor kelima, dia dalam bracket tu mesti conversion yang reaktor yang sekarang minus conversion reaktor yang sebelumnya. Maksudnya katakan kalau reaktor kedua is X2 minus X1. Let's say if it's a third reactor, dia akan menjadi FA0 in bracket X3 minus X2 per minus RA pada X3. Reaktor keempat, FA0 dalam bracket X4 minus X3, tutup bracket divided by minus RA at X4. So don't forget that part, okay? So become X2 minus X1 per minus RA at X2. So FA0 still 1.5, FA0 tak berubah sebab FA0 adalah initial molar flow rate yang masuk pada the very first reactor. Regardless kamu ada 10 reactor pun, yang FA0 tu masih FA0 yang sama, dia tak berubah sebab kita kira daripada the very first reactor punya molar flow rate. In bracket, X2 is 0.8, X1 is 0.2, so you divide by minus RA at your X2. Maksudnya, pada 0.8, my X2, my minus RA is 0.013. So I replace 0.013, you calculate, you get the second volume 69.23. Okay, so maybe you wonder, kalau reaktor pertama volume dia kecil saja kan, tapi reaktor kedua kenapa volume dia besar? Okay, logically, reaktor pertama hanya perlu mencapai 20% conversion sahaja. Reaktor kedua ni nak mencapai conversion from 0.2 to 0.8. You can see the gap of the conversion yang dia nak capai dalam reaktor kedua tu adalah sangat besar. So when the gap is bigger, naturally the volume needed is will be bigger lah because I need to convert a bigger conversion. Okay. Now, after you already obtained reactor pertama, reaktor kedua punya volume, what you need to do, you want to determine, right, whether it's suitable or not to be used, right? Okay, so you have to compare dengan available volume of the reactor yang kamu ada kat plant. Kamu kena ingat, volume yang kamu perlukan adalah 6 dan 69. You need 6 and 69. In your plant, the reactor volume is 50 and 50. Okay, so comparison, reaktor pertama, by right you can use. Sebab kamu hanya perlukan 6 sahaja dah boleh buat tindak balas tu. Your plant ada 50. Okay, done. So reaktor pertama, by right you can use the available one. However, for the second reactor, if you realize, you need at least 69.23 dm cube. Only you can achieve 80%. you can see tapi dalam plan saya, the second CSTR volume is only 50. So Miss tak cukup sebab kamu hanya ada 50 saja DMQ, tetapi sebenarnya pengiraan you need at least 69. So you can say that this configuration, although the first one can be used, but the second one cannot be used, the entire configuration tak boleh guna. Sebab untuk mencapai 80%, dia kena kedua-dua volume reactor tu fulfill. Baru kamu boleh guna reactor itu. Okay, so first part, CSTR, we can conclude the configuration cannot be used because the second reactor volume, calculated volume is bigger than the required, the calculated volume is bigger than the available volume. Okay, so CSTR we cannot use. So we go to the next example. Okay, we go to the next one, PFR pula. Okay, so CSTR kita dah done, kita dah buat kesimpulan. We go to PFR. Kita check. PFR boleh ke tak boleh? Okay, so PFR, kita kira juga volume dia. So the volume of the first PFR equals to FA0 integrating from 0 to 0.2 dx per minus RE. So why are we integrating from 0 to 0.2? Because in the first reactor, they are converting from zero conversion to 20%, 0.2. Okay, so you know kan kita kena convert jadi Simpson one-third rule. So become FA0 delta X per 3. So FA0 masih sama 1.5. You got no problem with this. What about delta X per 3? So kamu ingatkan kita kena divide the X into 3 points. So initial is 0, final X is 0.2. So our initial point 0, our final point 0.2. Our middle point or our middle X is 0.1. Titik tengah dia. So delta X is the difference, right? Difference between initial to middle X or middle X to the final X. So from initial to middle 0 to 0.1, the difference ataupun julat dia 0.1. 0.1 to 0.2 pun julat dia ataupun the gap or the difference is also 0.1. That's why your delta X is 0.1 divided by 3. Then in bracket, you have the 3 points. So you become 1 per minus RA at your initial X, which is 0, plus 4 per minus RA at your middle X, which is 0.1, and plus 1 per minus RA at your final X, which is 0.2. Okay, so done. Then kamu just look at the table, find the value. So at 0, my minus RA 0.053. At 0.1 minus RA 0.052. At 0.2 my minus RA 0.050. So kamu ambil je tiga nilai ni, you replace into the equation, you get the volume of 5.79. Okay, so first PFR nak mencapai 20% conversion, I just need 5.79 dm3. Okay, so again, kenapa kecil sangat? Sebab reaktor pertama tu hanya mencapai 20% conversion sahaja from 0 to 0.2. Smaller conversion, naturally reaktor yang diperlukan pun kecil sahaja. Dia tak payah reaktor yang besar kalau kita hanya nak mencapai small conversion. Okay, done. Okay, so we go to the second reactor. So again, sama konsep macam CSTR. Student tend to do mistakes at the second PFR. Or sometimes dalam exam, saya tak buat pun reaktor kedua kerana saya tanya reaktor ketiga, reaktor keempat dan sebagainya. So, you have to really understand concept. Okay, supaya, nak tahu you, test, exam memang takkan keluar bulat-bulat. Tapi, the understanding, kalau kamu faham memang no problem. Okay, so let us calculate for the second PFR. So, volume for the second PFR equals to FA0 integrating from 0.2 to 0.8. So kenapa? Because second reactor, I'm now converting from 20% to 80%. Kau bayangkan kita nak convert yang baki daripada 20% tu, kita nak convert sampai ke 80%. Okay, then dx per minus RE. Then Simpson one-third rule. So FA0, still the same, FA0 dia. Okay. Next, delta X per 3. So part ni yang biasa student akan buat mistake sebab dia lupa initial point dia dah bukan kosong. Initial point dia dalam soalan ni adalah 0.2. Your initial is 0.2. Your final is 0.8. Okay, 0.2, 0.8. So the middle X will be actually 0.5. Kalau kamu perasan, 0.2, 0.8. Titik tengah dia sebenarnya adalah 0.5. So your middle X is 0.5. So what about the delta X? So delta X is the difference, right? Between antara 0.2 to 0.5, berapa difference dia? 0.3. Kenapa kamu nak kira kat belakang? Daripada 0.5 kepada 0.8, from 0.5 to 0.8, the gap or the difference or julat dia masih 0.3. So that's why your delta X is 0.3. Okay, so part ni, make sure kamu ingat sebab part ni yang student has the tendency to make minor errors, which is sebenarnya, kalau kamu perasan sebenarnya okay, dia tak. If you really check, actually it's not necessary to do that kind of mistake. Okay, so delta X are done, divided by 3. Then in the back, okay, the bracket, we have 3 points. So 1 per minus RA at your initial X, which is 0.2, plus 4. 4 ni pun kadang-kadang sudah pun terlupa letak 4. So bila saya keep reminding ni bukannya apa, sebab memang this is a mistake that student tend to do. So macam sayang lah, sebenarnya student tahu nak buat benda tu. So it's a little bit sayang in my opinion kalau student dah tahu tapi dia tersalah mistakes yang macam ni. So that's why I keep reminding so that you don't do this kind of easy mistakes. Okay, so 4, don't forget sisa 1/3 row tu mesti 1, 4, 1. So 4 over minus RA at your middle X. So your middle X is 0.5. So 4 per minus RA when my X 0.5. Plus 1 per minus RA at my final X, which is 0.8 lah kan. So kamu cari, you look at the table again. Pada 0.2 berapa minus RA? Pada 0.5 berapa minus RA? At 0.8, how much your minus RA? And when you replace, you get the volume needed is 32.72. Okay, so now come back to the same thing. Kita kena tengok, boleh tak kita guna PFR ini? Tadi CSTR kita dah conclude tak boleh because second reactor tu volume yang diperlukan lebih besar daripada volume reactor yang sedia ada. What about PFR? Okay, so PFR yang kita ada 50-50 kan? Okay, yang kita kira yang we calculated for the first reactor is only 5.79. We need 5.79, we have 50. Definitely boleh. So reaktor pertama biasanya takkan ada masalah. What about second reactor? So second reactor, what we need is 32.72 and I have 50. Okay, definitely reaktor kedua pun kita boleh guna. So dalam case ini, for this PFR configuration, both reactor volume calculated is lesser than the available volume we have in the plant. Hence, we can conclude the PFR can be used in the plant. Okay, so let's say kalau soalan dalam exam ke dalam test, you have to really dah kira, kamu kena tulis jawapan dia. Kenapa kamu kata, okay, PFR boleh digunakan. Kenapa CSTR tak boleh digunakan. Okay, so you can see this is a problem solving question of which untuk kamu menjawab persoalan dia, kamu kena calculate from the numbers, then you can answer whether it's feasible or it's not feasible. Okay, so as usual, I will give you about 2-3 minutes for you to try to attempt if you have the things in front of you. I will switch off kejap camera and volume. I will come back in 2-3 minutes time. Okay, so please do it if you have time at the moment. Alright.